Hi, everyone. This week, we're going to talk about multiple regression. Now, multiple regression models build upon all of the knowledge that you covered in the simple linear regression chapter. The primary difference between a multiple regression and a simple linear regression is that multiple regressions have multiple independent variables. This is the basic form of a multiple regression model with k independent variables. What do we mean by k there? Insert any positive number for k, and you can have that many independent variables in a multiple regression model. As with simple linear regression, beta naught represents your constant in the model. Beta sub 1 represents the regression coefficient that goes with your first variable. Beta sub 2 represents the coefficient that goes with your second variable, all the way out to beta sub k, which goes with your kth variable. At the very end, you see your error term. Now, this error term is actually implied and exists with the simple linear model too. In fact, you probably saw it listed in your textbook a few times. But that error term is not part of what you use to plot your line. Your error term instead would be in the simple linear model what you use to plot confidence intervals as a band around your line. And that's the best way really to think about your error term. Think of it as the amount of noise that creates a range of numbers that you're confident that your real regression line falls within. Let's look at some examples of data. For this chapter, we're only using SPSS because it is far easier to work with when you get to multiple regression models. Excel can do it, but it's quite the mess to work through. This is a data set that came with your textbook. It's data from a vineyard where they have a quality score for each of their wines, as well as counts of the contents, such as fixed acidity, volatile acidity, citric acid, and so forth. All of the data is purely numerical, and there are a variety of scales of data. Now, I know very little about wine, just enough to know that all of these things are independent variables that can affect the quality. So let's see if they do. We'll go to Analyze, Regression, and once again, Linear. I'm going to take the quality variable and move it into the dependent variable space, and all of the other variables and move them into the space called Block 1. Block 1 is the place where all of your independent variables belong. When I hit OK, we're given our regression model. Because we have multiple independent variables, we're now going to look at this adjusted R-squared, which tries to attenuate for error that may be presumed by independent variables placed into the model that actually don't fit well. We see that our F-test is significant, so our null hypothesis that there's no fit or no prediction is rejected. And then we get down here to the coefficients. As always, we start by looking at our significance level. Here we see that only 2 of our variables, chlorides and alcohol, were statistically significant predictors of quality. Now, there's some debate here as to whether this should be the last step of your model test or not. Some scholars feel that you should leave all of these variables in your model, even those that are not statistically significant predictors, because they may be accounting for such a small amount of variance that it's not meaningful in practical terms, but they are still realistic pieces of the model. Other scholars say that leaving all of those statistically insignificant predictors in the model just obscures your prediction of how much you know is affecting the dependent variable versus how much is error or noise. So some scholars believe that a necessary second step is to go to Analyze, Regression, Linear, and then remove all of the variables from your model that are not statistically significant predictors. In this case, we would be looking at just chlorides and alcohol as predictor variables. Now remember, our adjusted R-squared was 0.42. When I run this analysis anew with only the statistically significant predictors, now our adjusted R-squared is 0.40. So we've gone from explaining 42% of what was happening to only 40% of what's happening. Personally, I don't have a strong opinion either way as to whether you take the second step to pull out the statistically non-significant predictors or not. And the reason I don't have a strong opinion of it is because it doesn't change much of the variance explained. And in the end, my conclusions are still the same, that of all the independent variables tested, we find that only chlorides and alcohol help us predict the quality of the wine. So whether when you run a multiple regression, you decide to leave all of your independent variables in, or you want to narrow your model down to something smaller like this, I leave that up to your judgment. Let's look at one more example. This is another data set that comes with your textbook. This is a data set of purchase history from Pizza Hut. The data is a bit old, so it only reports gender as male or female. It produces the price per large pizza and indicates whether or not someone purchased after hearing the price. With this data, we can see if gender and price predict purchase behavior. But we would need to analyze this data differently than we did the last data set. And that's because our purchase variable is actually categorical. With multiple regression, we are able to run analyses that predict categorical variables as long as there are only two categories. We code these categories as 0 meaning none and 1 meaning all. So 0% align with purchase or 100% align with purchase. So let's look at an example of how to run a regression with a dependent variable that is categorical. Again, we go to Analyze and Regression. But here, instead of going to linear, we're going to go to binary logistic. And that's what this is. This is a logistic regression, a specialized regression that allows you to predict a dichotomous variable. We're going to move purchase into the dependent list and gender and price into our block and hit OK. This output is a bit different than what we've seen so far. And what we're really interested in is this table at the very bottom of the output. Variables and their equation. Again, we look at our significance level and identify variables that are associated with a p-value of less than 0.05 to see what is accounting for variance. The end product of logistic regression is something called odds ratios. It allows you to predict the probability of an independent variable causing a change in the dependent variable. Here, we see that gender is not a statistically significant predictor, but price is. Here where it says EXPB, this is our odds ratio. You read this odds ratio as for a 1 unit increase in this independent variable, we expect the dependent variable to change by this %. So essentially we see here that for every dollar increase in price, we expect purchase intention to drop by 20%. Again, because this represents a change multiplicatively. Any odds ratio less than 1 is predicting a drop in the dependent variable, whereas odds ratios greater than 1 predict an increase in the independent variable. Odds ratios associated with decrease also have a negative beta weight. So this is an example of how you would use a multiple regression technique to predict change in a categorical variable. So this wraps up our discussion on the chapter. I hope these examples help to illustrate some of the concepts. Please let me know if you have any questions.